Hi, my students. First, I'd like to invite the God to overcome COVID-19 epidemic. Say Amin. This is the lecture number 6 in applied statistics. This lecture contains 3 points. Number 1, the empirical rule, and I believe that you study this rule in second year, but I will review this rule. The second point is how can you standardize the normal distribution data. I mean the rule of Z-score. How can you create or compute the Z-score? And the third point is some applications of normal distribution. Okay? The first point, the empirical rule. The empirical rule, as we studied before, apply it to the bell-shaped curve. This empirical rule based on the standard normal distribution. Okay, so we can verify the empirical rule as follows. Look at this. Number 1, the total area within one standard deviation of the mean is 68.26%. So between one standard deviation around the mean, the area under distribution equal about 68%. Okay, from minus Z to plus Z, from minus Z, from minus sigma to plus sigma. Okay, this area is given by the difference between the area to the left of Z equal 1. If we deal with the standard normal distribution, this area will be from Z equal 1 to Z equal minus 1. Okay, so here instead of sigma, Z equal minus 1, and here instead of sigma, Z equal 1, and instead of mu in the standard normal distribution, the mu equal 0. Okay, so for the standard normal distribution, this area, well, between minus 1 and the plus 1, around the 0. But for any other normal distribution, this area between minus sigma and the plus sigma around mu. Okay, so the second rule is the area between minus 2 sigma and plus 2 sigma around the mean equal 95%, or about 95%. This area from 2 sigma to minus 2 sigma. Okay, if we deal with the standard normal distribution, this area will be between 2 and minus 2. Okay, around 0 or around the mean. Okay, the third rule is the area under distribution between 3 sigmas and minus 3 sigmas equal 99.7%. 99.7%. Okay, so if you wanted to get this area only between mu and 1 sigma to the right, you have to divide this area by 2. Okay, if you want to get this area from mu to 2 sigma, then divide 95%. If you want to get the area between 1 sigma and 2 sigma, okay, so divide this one by 2 and divide this one by 2 and subtract this area from this area, okay, subtract this by this. So when z equal 1 or 2 or 3 or z equal -1 or -2 or -3, you don't need the table of z. You don't need. Why? Because of the empirical rule, okay, because of the empirical rule, right? So as shown in the above figure, this area is computed using the standard normal table, okay, which equal 0.84 minus 0.158, okay, equal 0.6826, okay. And is defined as bz larger than -1 and less than 1 equal 68% or about 68%. Using a MATLAB program, you have to use the function norm spec and the distance or the interval between -1 and 1, and mu sigma here, mu equal 0 and sigma equal 1, okay. You can omit this 0 and 1 because the norm spec is applying by default to the normal distribution, the standard normal distribution, okay. If we deal with any other normal distribution, you have to put mu and the sigma, okay. So this is the first rule. This is the shape and this is the probability between z equal 1 and z equal -1, right? The second rule, the total area within 2 standard deviation of the mean is 0.95%. This area, the difference between the area to the left of z equal 2 and the area to the left of z equal -2, okay. So p z larger than -2 and less than 2 equal 95%, okay. Like this. Okay, so using MATLAB, with the function norm spec, the species is -2 and +2, and you can omit 0 and 1 or write 0 and 1, okay. So this area equal 0.9%, this area between 2 and the -2, okay. The area under the curve between 2 units of standard deviation around the mean, Rule number 3, the area between z equal 3 and z equal minus 3, this area equal 99.7%, like this. Okay, using MATLAB, the function norm split between minus 3 and the plus 3, and you can omit 0, 1 or write 0, 1. Okay, so this area equal 0.997%. This area, you know that most of the area under distribution lie or located between minus 3 and plus 3. Okay, right? Again, note that only a specific bell-shaped curve represents the normal distribution. Okay, so you can conclude that. Only a specific bell-shaped curve represents the normal distribution. Okay, now we can state that the bell-shaped curve that contains about 68.3% of the total area within one standard deviation of the mean, and about, okay, so the bell-shaped eligible for the empirical rule is the normal distribution. Okay, so not all bell-shaped curves represent a normal distribution. This only a specific bell-shaped which eligible for apply the empirical rule. Okay, like this. The standard normal distribution table goes from z equal minus 3.49 to z equal 3.49. Okay, so any number less than this, when z equal any number less than minus 3.5, the area under distribution will be 0. And for any z larger than 3.5, the area under distribution will equal 1. Okay, so if we need to find the area to the left or smaller value of z, we can assume it to be approximately 0. Okay, approximately 0. Okay, for any z less than this value, the area equal 0. If we need to find the area to the left of or larger number larger than 2.5, we can assume it's approximately equal 1. Okay, the following example illustrates this procedure. Example 4. For the standard normal curve, find the following probability. Number 1, probability of z larger than 0 and less than 4.5. Okay, so the table will not include this value, and this value is larger than 3.5. Is larger than 3.5. Okay, time. The number 2, the probability that z less than minus 5.4, and we said that the table end at minus 3.5, so this value is less than minus 3.5. So the area under distribution to the left of this value equals 0, and here the area to the left of 4.5 equal 1, and the area between 0 and 4.5 equal 1/2, okay, equal 0.5, okay. Solution by hand. Okay, the probability that z is larger than 0 and less than 4.5 equal 1 minus 0.5 equal 0.5. Okay, half of the area under the curve, 1/2 of the area under the curve. By MATLAB, these spaces, the limitations or the interval, the lower point is 0 and the upper point is 4.5, and mu equal 0 and sigma equal 1. You can write or omit these values, 0 and 1. So the probability equal 0.5, like this, okay, 0.5. This one from 0 to 4.5, this area from here to here, okay. B, but the same way, the probability that z is less than minus 5.4 equals 0, because the value minus 5.4 is not involved in the table, okay. So from minus infinity to minus 5.4, this will be a 0, this will be 0, or a very small number like this, 3 divided 8 zeros, a very small value, and extremely equal 0, or approximately equal 0, like this. You cannot see the area under distribution here. You cannot see this. The second point is standardizing a normal distribution. Standardizing the normal distribution means that we have to compute the standard normal value, or change the values of x to be values of zeta or z. So how can you change or transfer the value of any observations to be z score, okay? As was shown in the previous section, table 1 of appendix can be used to find areas under the standard normal curve, However, a real world applications of continuous random variable may have a normal distribution with values of mean and standard deviation that are different from 0 and 1 respectively. Okay, so how can you change or transfer the normal distribution to be standard normal distribution? Standard normal distribution with mean equals 0 and standard deviation equal 1. So the first step in such a case is to convert the given normal distribution to the standard normal distribution. This procedure is called standardizing a normal distribution. So here, what's the mean of standardizing normal distribution? Transfer any normal distribution to be a standard normal distribution with mean equal 0 and standard deviation equal 1, right? The units of normal distribution, which is not the standard normal distribution, any normal distribution, are denoted by x, as we learned before. We know that the units of the standard normal distribution are denoted by z. So how can you transfer x to bz? Okay, for a normal random variable x, a particular value of x can be converted to its corresponding z by using the formula z equal x minus mu over sigma for population, or z equal x minus x bar over s for sample. Okay, where mu is the population mean, sigma is the population standard deviation, x is any observation, x bar is the mean of sample, and the s is the standard deviation of a sample. So the z-score can be defined as the number of standard deviations x's from the mean, x's from the mean, or the difference between the observation x and the mean measured by standard deviation, units. Okay, if the value of an observation is greater than the mean, if x is greater than mu or x bar, its z-score will be larger than 0. Okay, so z-score will be positive if x is larger than the mean. Z will be positive. When the value of observation is less than the mean, its z-score will be negative. Okay, thus to find the z value of an x value, we calculate the difference between the given x value and the mean, and divide the difference by the standard deviation. If the value of x is equal to the mean, then its z equal to 0. Okay, if x equal to the mean, so x minus mu or x minus x bar equals 0. Okay, so z equals 0. Note that we will always round z values to 2 decimal places as the table given, because the table of standard normal distribution puts z equal only 2 decimal points, only 2 decimal points, as we did before. The z value for the mean of a normal distribution is always 0. So mu equals 0 for the standard normal distribution. The following examples describe how to convert x values to the corresponding z values and how to find area under the normal distribution curve. Z score. The function z score is a standardized z score. Okay, so this function syntaxes are z equals z score of x, or z score of x and flag, or z score is x and flag and the dim. This one for any data, whether x is a vector or a matrix. This one is computing z score for a sample or for a population. For a sample, put flag equals 0 or omit flag. For population, put flag equal 1. Why? Because the standard deviation as for a population is different from the standard deviation of the sample. When computing the standard deviation for a sample, we divide, or the denominator will be n minus 1. For population, the denominator will be n. So z score for population is not equal z score for a sample. Okay, z score for population, the standard deviation, is computing using n in the denominator, but in the sample using n minus 1 in the denominator. Here, them for matrices, for a matrix. If we deal with a matrix, then them equal 1 for columns, or omit them, and them equal 2 for rows. So if you want to get z score for rows, put them here equal 2, right? Okay, z mu sigma equals z score of x, for example, or any one of this. Okay, if x is any data, then z score and mu and the sigma, mu for this data and sigma for this data. If you don't know the mu and the sigma of data, you can get z score and the mu and the sigma at the same time, right? Okay. Example number 5. Example number 5. Let x be a continuous random variable that has a normal distribution with the mean of 40 and the standard deviation of 10. Convert the following x values to z values and define the probability to the left of these points. Number A, x equal 45. B, x equal 25. Solution. By hand, the z value for x equal 45 is computed as follows: x minus mu over sigma, x equal 45 and mu equal 40 and sigma equal 10, so z equal 0.5. Thus, for x equal 45, z equal 0.5. Note that the z value of 40 is 0. Okay? So if you substitute 45 by 40, then 40 minus 40 equals 0. So z value for 40 equals 0. Okay? The value z equals 0 the value z equal 0.54, x equal 45 indicates that the distance between mu equal 40 and x equal 45 is 1/2 of the standard deviation. So the difference between 40 and 45 equal 5. 5 divided by 10 equal 1/2. So consequently, we can state that the z value represents the distance between mu and the x in terms of standard deviation. Right? Okay. Px less than 45 equal Pz less than 0.5. From the table you can get this probability like this. Number B, when x equal 25, then z equal minus 1.5. Okay? So the probability that x is less than 25 equal the probability that z is less than minus 1.5 equal 0.066. By MATLAB we will use z score if we want to compute by hand. So z1 equal x1 minus mu divided s, where x1 equal 45 and mu equal 40 and s equal 10, like this. So by calculator or by computer or by hand, z1 equal 0.5, and for x2, where x2 equal 25, z2 equal x2 minus mu divided sigma equal minus 1.4. So using the norm spec function, the first spaces are minus infinity and 45, mu and sigma. Here you have to put or to write mu and sigma, because this is normal distribution, not a standard normal distribution. So mu equal 40 and sigma equal 10, then the probability is 0.69. For the second probability, the spaces or the limits is between minus infinity to 25, and put mu and sigma. This probability equal 0.07. As you see, this is the first probability when x equal 45 to minus infinity, and this is the second one when x equal 25 to minus infinity. Okay, example 6. Here the mean of the standard normal distribution is 60 and the standard deviation is 10. Then we need to compute zeta. The first probability is probability of x is greater than 60 and less than 65. Number 2, probability that x is larger than 70. Number C, probability of x is less than 55. Number D, the probability of x greater than 55 and less than 70. Solution: Z for A equals 60 minus 60 equals 0 divided by 10 equals 0. So when x equals the mean, Z equals 0, like this. Okay. So Z for 65, Z equal 65 minus 60 divided by 10 equal 0.5. Okay. So the probability that x is larger than 60 and less than 65 looks like the probability that z is less than 0.5 minus z less than 0. Okay, so this like this minus this. Okay, the first is zeta equals 0 and the second zeta equal 0.5, and this probability is the same as P of z less than 5, this one, minus the probability of z less than 0, this one. Okay, so the probability that z equal to minus 2 minus 5 minus the probability that z equal 0. Okay, this area minus this area. Okay, so the first area is 0.69, the second area equal 0.5, so the difference is 0.19. Number B, Z for x equal 70, Z equal 1, and for the probability that x is less than 70 looks like instead of x put z equal 1, looks like b z less than 1. Okay, so this probability equal 1 minus bz, here bz greater than 1, greater than, so lie in the upper area, upper region, here to the right of z, z greater than 1, so the probability that the value of z is greater than, not less than. So this value can be computed by the inverse. Inverse means 1 minus bz less than 1. Less than 1. This probability is 0.15. And number C, the probability of 55 for z when x equal 55, z equal minus 0.5. This value this one. Okay, so the probability that x is less than 55 equal the probability that z is less than 0.5. Okay, so from the table this probability equal 0.3. So the probability that x is larger than 55 and less than 70 looks like the probability that z is less than 1 minus z is less than minus z is greater than minus half. Okay, by MATLAB, just write these spaces or the limitations of every probability like this. This is the first one. The second one, greater than 70, means from 70 to infinity. Less than 55 means that from minus infinity to 55. And between 55 and 70, this probability equal 0.53. Okay, so it's very easy to compute the any probabilities using the norm-spec function. Okay, this is the figures for those probabilities. Applications of the normal distribution. This is the third point, contains some applications for the normal distribution. Example number 7. Suppose that the current monthly pocket money for all college students have a normal distribution with a mean of 300 pounds and standard deviation of 50 pounds. Find the probability that the monthly pocket money for a randomly selected college student is between 270 pounds and 420 pounds. Okay, so here the mean is 300 pounds and the standard deviation is 50 pounds. And now we have to compute that a selected student has a pocket money between 270 and 420. By hand, for x equal 270, z equal 0.6, and for x equal 420, z equal 2.4. So we want to compute the probability that a randomly selected student has a pocket money between 270 and 420. This means that Z will between minus 0.6 to 2.4. So we have to compute this probability from Z equal minus 0.6 to Z equal 2.4. Like this. The probability that X is greater than 270 and less than 420 equals the probability that Z is greater than minus 0.6 and less than 2.4. This probability equal 0.71. By MATLAB, the spaces will be 270 and 420, and mu equal 300, sigma equal 50, then the probability equal 0.71. And this is the shape or the area under distribution. Example 8. A baby car is one of the many toys manufactured by Ayman Corporation. The assembly times for this toy follow a normal distribution with the mean of 45 minutes. So the mean is 45 minutes, the mean of assembly of the toys, and the standard deviation is 5 minutes. The company closes at 5 p.m. every day. If one worker starts to assemble a baby car at 4 p.m. 4 p.m. means before closing by 1 hour. Okay, the company will close at 5 p.m. and the worker start to assemble the baby car at 4 p.m. Okay, what is the probability that she will finish the job before the company closes for the day? Okay, this means that what's the probability that she will finish during 1 hour from 4 to 5. Now this is mu equal 45 minutes and sigma equal 5 minutes. The probability will be x here equal 1 hour. 1 hour means 60 minutes. Okay, 60 minutes. So transferring 60 minutes, transferring x to be z. Okay, so when x equals 60, z equal 60 minus 45 divided 5 equals 3. So z equals 3 for x equal 60. The required probability is given by the area under the standard normal curve, that x is less than 60 means z is less than 3. This area from the table equal 0.998. Okay, so using the empirical rule, you can say that the area between 3 and minus 3 equal 997%. So you have to divide this area by 2 and add one half. Okay, so z equal or less than equal to or less than 3 means z from minus infinity to 0 and or plus z from 0 to to 3, from 0 to 3. Okay, this will be 998%. By MATLAB, just put the spaces or the limits minus infinity and 60 means 1 hour, and mu and sigma, this will be 0.998%, and this is the area under distribution. Example number 9, it's the same as number 8. Okay, here the mean is 250, and we want to compute the area under the curve between 230 and 244. This probability, after transferring, get the probability by the same way, like this. This is the probability that x is greater than 230 and less than 245 after transferring z to x. This means that the probability that z is greater than minus 2.5 and less than minus 0.75, negative 0.75. Okay, like this. This is the mean, and we want to get this probability. Okay, so transfer x equal 252 and transfer x equal to 258. Here z equal 0.25 and here z equal 1. So compute the probability that x equal to or larger than 252 and equal to or less than 258. That looks like z is greater than 0.25 and less than 1. By MATLAB, put the spaces like this. It's very easy, between 230 and 244. This is the first one and this is the second one. This is the area for the first and the second, and this is another example. Okay, so this example is as you see, computing the probability of x is less than 36. It looks like the probability that z is less than minus 2.4. Okay, by MATLAB, put the limits by minus infinity to 36. This probability is equal to 8%. Okay, like this. Determining z and the x using a b will be cancelled. So this is the fourth point in this chapter. You can cancel this point as you see. Cancel it. Okay, so we will stop here to this point, and in the next week I will told you about the research or the examination or anything else. Thanks, and see you later.